fundamental theorem of arithmetic. Fundamental theorem of arithmetic. Statement: every positive integer n is greater than 1 can be expressed as a product of primes. This representation is unique apart from the order in which factor occurs either n is prime or n is composite. So here, before going to prove, I will take here example for 120. Here I take 120 here, 120 expressed as product of primes, so or factors of primes. So you can 2 is a prime number, so I'll divide it by 2. So what do you get here? You'll get 60 and 2. So what do you get here? 2 means it will get 30, and if you divide by 2, so we will get 15, and again if you divide by 3, you will get 5. So if you divide by 1, you will get remainder is 1. Until when you get remainder, you have to stop it. So what do you get here? 2 cube, 2 into 2 cube into 3 to the power of 1 into 5 to the power of 1. So forget about the power. What I get here? 2 is also prime, 3 is also prime, 5 is also prime. So 120 can be expressed as 2 cube into 3 into 5. So 120 can be expressed as in prime factor. So this is the required solution. So for this one, you're writing here general proof for this one. So here now, what is composite? Here composite means n has a factor other than 1 and itself. Here example, here 2 is a prime number, so you'll get 2 only. 3 is also prime number, you'll get 3 only. And here you'll get 6. Suppose if I take 6, 196. So what are they here? N has a factor other than 19 itself. 19 itself means 6 is there, is divided by 6 only. So other than this one, here you can write 2 into 3. 2 3s are 6. Here 3 into 2. So this also possible. So other than 19 itself means you will get 2 composite here. So these are your composite. Okay, so now here, now I'll go from proof here. So here 2 is in prime, 3 is also prime, so 5 is equal to 5, so 5 is also prime, and 7 is also prime, and 11 is also prime, 13 also prime, 17 is also prime. So what are the composite numbers here? 6 is there, and here 4, 6, 4, 6, and what do you get? 8, 9, 10. So these are your prime numbers, right? Or composite numbers also you can tell. So here, if n is prime, if n is prime, here if n is prime, here what do you have to prove? Product of primes here, cofactor of primes. So there is nothing to prove here if n is prime. So if n is prime, there is nothing to prove. Suppose here if I take composite numbers, if I take here composite numbers, what I get here? If n is composite, then there exists integer d such that d divides n, and 1 is less than d and less than n. 1 is less than d and less than n. So here how you got this one means, suppose I will take d is equal to, I will take 6 here. So 6 can be written as what I get here, 2, 3, 3 2s are 6. So 2 divides 6 and 3 also divides 6, right? So here 1 less than, so what I taken in here, n is equal to 6 taken, so I taken here, I wrote here 6 here, 6 here. So what do you get here? D is, here you can take 2 or 3 here, look at here. So here I taken n is equal to, n equals 6, so I taken here n is equal to 6. 6 can be expressed as 2 3s are 6, so we'll get both are prime here. So both are prime, so we get 2 divides 6 and 3 divides also 6. So this can be written as here, in between 2 is less than 1 and in between 1 and 6. So if I take 3 also, what I get? 3 is also between 1 and 6 only. So that means for always it should be 1 is less than d and less than 1 is less than d and less than n. So take any number of here values for n composite numbers. If you take it for if you take it, another one is 12. So 12 can be written as what you get here, 2 6, right? So here okay, I'll take these two numbers only. So if I take these two, if you compare for this one, what I get? 1 is less than, if 2 divides 12 also, right? 2 is less than, what is n here? I taken 12. So here what I get now? So 1 to 12, 2 here it lies between 1 to 12, 2 is lies between 1 to 12 only. So I taken in here this one as like this. So next line, among all such integers all such integers d, choose choose p1 to be the least least least, then p1 divides n comma 1 is less than p1 and less than n. So here suppose here in if I take 6, which one is here? 2 and 3, right? So which one is this? 2 is the least. So if I take 2 is least means what do you get? In between 1 and 6, here you get 2 lies between 1 and 6 only, right? So I wrote here p1 is least here, so I taken is here, 2 is here, so p1 lies between 1 and n. So here also 2 is lies between 1 and 6, n is 6 here. So next, if p1 is not a prime, if p1 is not a prime, it is a here. If p1 is not a prime, then you have to again, if n is composite, again you have to apply this method. So it is a composite, there exists integer q, such that q divides p1, here 1 is less than q and less than p1, here p1 is less than what you get? N. So that implies that what you get? Q divides p1 means here p1 divides n, right? p1 divides n by using this one, p1 divides n. So this implies q divides n. So where 1 is less than q and less than n, q is lies between 1 and n. So which is contradicts p1 is least, which contradicts p1 is least. Here p1 is always least here. So therefore p1 is a prime. So p1 is a prime. Now here, so if p1 is a prime means what do you get here? N equals p1 into q1, because here p1 divides n here. So okay, now if q1 is a prime, then there is nothing to prove. Here if you get confusion, I'll give an example here. So I will take 36 here. So 36 here, 36 can be written as 2 18s are. Here 2 is prime but 18 is not an prime number. So again you have to convert 18 can be written as 3 6 are 18. So you get again here prime number, but 6 is not a prime number. So again you have to convert this one into here prime. So when you get prime, you will not get no problem here, but when you get composite here, so we'll get a problem. So what I'll do here, I'll convert this one into prime number. So here now again you have to convert this one 6 is because 6 is not a prime number. So 2 into 3 into, so 2 into 3 you can write. So 2 square into 3 square. So we get a prime here, product of primes here we get. So like that, here also theorem goes where n is here p1 is prime. So here if q1 is prime, no problem. If q1 is not n prime, then you have to convert it into prime here, then you have to prove. So here now if q1 is composite or not a prime, both are same, composite or not a prime, so then there exists d1, I will call it as d1, such that d1 divides q1, d1 divides q1. Here you have taken, here look at here, so here if n is composite, then there exists integer d such that d divides n. So same it is d1 divides q1, and here d is lies between 1 and n, right? So and here what do you get? 1 is less than, what do you get here? d1 is less than q1. So after that what is said? Among all such integers, among all such integer d1 choose p to be the least, then p2 divides, what do you get? p2 divides q1. So then q1 p2 is lies between 1 and n. So this implies what I can write this one. So this is q2, q1 lies between q1. So this implies that what I get, n equals here p1 into p2. So into what I get, q2. Here q2 will get. However, this one means here divisor property. So what do you get here? Here p2 divides q1 means here q1 equals p2 of some another integer q2 you can write. So a divides b means b equals k times of a, right? Like that you written here. So this implies that what you get, q1 equals p2 into q2. So if we substitute for above equation here, equation star, so what you get, n equals p1 into what is q1, p2 into q2. So we substitute here. So here if p1 is prime, okay, no problem. p2 is also prime, no problem. If q2 is also prime, the process will be stopped. If q2 is not an prime, opposite means we have to continue the same process. So here the decreasing, so the decreasing sequence here n is less than q1 and less than q2 and sorry, not less than, here n is greater than q1 and greater than q2 and here greater than q3, so on is greater than 1. Here cannot continue to infinity, infinitely or infinity, because here it will be decreasing sequence, right? You can't continue up to infinity. So that after a finite number of after a finite number of steps, here q suffix k minus 1, q suffix k minus 1 is a prime. Here after a finite number of steps, here q suffix k minus 1 is a prime, and it has p suffix k. It has p suffix k. This leads to prime factorization n equals t1, p2, p3, p4, so on up to p to the power of k. So this proves the theorem, but we have to prove another one. What is that one? Here you proved product of prime or factorization, prime factorization or factorization of primes. You prove that one, but after this represent is unique apart, so you have to show it is an unique. So next you have to prove it is an unique. So here to prove this second part of theorem, that is uniqueness of prime factor. So here let us suppose that the integer n can be expressed as the product of primes in two different ways. Say here n equals p1, p2, p3, so on up to I take pr. I take this one as one different way, primes here, equals another one is q1, q2, q3, so on q suffix s. So this implies that r is less than equal to s. I will tell r is less than equal to s when p i's and q i's are primes primes in written in increasing magnitude increasing magnitude, so that if you here increasing magnitude, so means if you write p1 is less than equal to p2 and here is less than equal to P3 is less than equal to P4, it will be continuing, is less than equal to P suffix R. So that implies here equals, this can be written as Q1 is less than equal to Q2, less than equal to Q3, so on, is less than equal to Q suffix R. Q suffix, this one is Q suffix S. So since here P1, this is also prime and here this also prime, means P1 here P1 divides Q1, Q2, Q3, Q4, so on, Q sub. Yes, that means here example here if you take P1 is 2 means here we'll go for q factors. Here q is 3, 5, 7, somewhere you'll get 2 means it divides here, it divides 2, so that means it divides somewhere, that's all. P1 is divides somewhere in q, so this implies that P1 divides q suffix k. So for k equals 1, 2, 3, so on up to s I taken here. So then this implies that q1 is less than equal to q suffix k. Q suffix k means I taken here. I'll write here p q1. Here you can take it q3 or q4 anyone. Here 5 4 3 5 7 3, here 3 7 5, both are same. Here this is p1 at p2 p3, so what I get here q1 q2 q3, so p1 is equal to what I get here 5 is there, so you get q3, you can write p1 equals q3 also you can write. Here P2, what you get P2 here will get Q2, so what you get P1 equals, you can write P3 equals what you get Q1. This is also true. So for my convenience I'm taking P1 divides Q1, P2 divides Q2, P3 divides Q3, P4 divides Q4, like that I'm taking. So P1 is less than equal to Q, can right? So this implies that P1 equals Q1. So you prove this one. So like this gives here, this gives P2, P3, P4, so on up to P suffix R equals what you get. We taken already P1 and Q1. So what is remaining here? P1 and Q1 is remainder. So what you get P2, P3 up to PR and Q2, Q3, Q4 up to Q suffix S. It will be remaining. So suffix S. Now here Now, what is it here? Now, now here, continue this process, we get here P2, we get P2 equals Q2, P3 equals Q3, P4 equals Q4, so on. So here P2 equals Q2 and here P3 equals Q3, P4 equals Q4, it will be continuing. But what you get here? R and S. You have to check it. You have to check it for P suffix R and Q suffix X because here we taken R is less than equal to S. So first case you take R is less than N. Check it what you get, and here second one R equals S. What you get here? You have to check. So now if R is less than S, then here R is less than N means what you get? Here you have P1, P2, P3, so on, PR divides here Q1, Q2, Q3, so on. You'll get QR here. Next you'll get QR plus 1, QR plus 2, QR plus 3, so on. You get QR, Q suffix SCL. So here this divides this divides this divides this, and here P suffix R divides Q suffix R, but here it will be remainder here. So what is in here? 1 divides, what you get? QR suffix 1, Q suffix R plus 2 and Q suffix R plus 3, so on. You will get Q suffix X. So 1 equals, what do you get here? QR plus 1 and here Q suffix R plus 2, so on up to here Q suffix S will get. So it is not possible because here which is not possible. So here something it will get remainder here. So this is not, which is not possible, or this is not possible. So this case is not possible means what you get here? R less than S means then you can write 1 equals Q suffix R plus 1, Q suffix R plus 2, Q suffix R plus 3, so 1 Q suffix S will be. So which is not possible. Which is not possible. So here if R equals S, if R equals S means what do you get here? P1, P2, P3, so on. You will get P suffix R divides Q1, Q2, Q3, so on. If you put S is equal to R, you will get Q suffix R. So this P1 divides Q1, P2 divides Q2, P3 divides Q3, so on. P suffix R divides Q suffix R. So you'll get 10 prime factors only for these two. So this case is possible. So what do you get here now? So here P1, here P2, P3, P4 equals, what do you get? Q1, no, I'm sorry, P1, P2, P3, so on. P suffix R equals, what do you get here? Q1, Q2, Q3, so on. Q suffix S. So R equals S means both are equal. So that means, so what do you get? P1, this implies P1 equals Q1, P2 equals Q2, P3 equals Q3, so on, P suffix R equals Q suffix S. Thus n has unique prime factorization. Sorry. Factorization. So this proves the theorem.